This is Unit 4 in the Ford Maintenance Training Series on Troubleshooting Strategy. Now, in the last lesson, I talked about visualizing component blocks and the arrows or lines that join them together to show the dependency or flow relations among components. I talked about inputs and outputs and about showing system flow going left to right. Here's a sample machine system flow diagram that illustrates all of these ideas. This is the kind of system flow picture you need to visualize to be able to do a good job of logical troubleshooting. But how do you visualize such a system diagram? Well, if you've been working with a system for a long time, you may have such a diagram in your head. If you don't, you'll need to know all about the system's parts and how they work together. You may need to sketch the system flow diagram. It need not be pretty, but must be accurate. Now, in this lesson, I'm going to demonstrate how to visualize a system flow picture and provide some practice. Now, what will you need to know or find out before you can visualize a system flow diagram? Well, since the flow diagram connects the system inputs to the system outputs, you'll need to know the inputs and outputs. Second, since the component blocks are replaceable units, you must find out which parts of the system are replaced and which are repaired. Third, you must know the sequence or dependency of the connections between components. This means knowing where each component gets its inputs and where its outputs go. Let me say a few words about each of these information requirements. Inputs first. I'm going to discuss some types of inputs. Some are obvious, others are not so obvious. But make sure you identify all of the inputs. Now, one input of almost all systems is energy. This kind of input includes electrical energy and mechanical energy, which might be supplied through a rod or gears, as well as any kind of fuel. Then there can be fluids, which lubricate or cool the system, such as grease, oil, water, etc. Also, there could be materials to be handled. Systems can usually tell when this input is lacking, like in a conveyor system, but sometimes you can't. For example, a good home plumbing system could appear to fail if it were only lacking the material to be handled. You might suspect a leak when the real problem is at the water company. Another type of input can be signals or data. Systems are often designed to talk to each other, to transmit and receive data or information. Of course, a radio receiver has to have a transmitted signal before it can operate. Another system might require timing signals to tell it when to perform various operations. The last type of input I'll cover is operator actions. The lack of this type of input is often easy to detect. You detect it by trying to reproduce the symptoms reported by the operator. If the system runs perfectly when it is operated, there's either an operator error or an intermittent fault. And by the way, intermittent faults are the hardest kinds of faults to find. If the fault is not present when you are troubleshooting, and if you can't identify the conditions causing the fault, you won't be able to find the malfunction. But I'm getting off the point. The point is that you need to know the system inputs and outputs. Now, I've just mentioned the kinds of inputs you ought to look for. The types of outputs will be much the same as the types of inputs, except that operator actions will become operator information. This is the status information supplied to the operator by the system. Usually, the system tells the operator how things are running by means of indicators, meters, warning lights, etc. Now, when I talk about energy sources, I include many different kinds of energy, including electricity, heat, sound, light, and mechanical motion. Notice that the last output is called waste products. The washing machine puts out dirty water. A car puts out exhaust gases. One example you're probably familiar with is the used cutting oil put out by many machining operations. Okay, let's say you've identified the system's inputs and outputs. What else do you need? Well, as I said before, you'll need to know what the replaceable components are. These components are the blocks in your system flow diagram. To coin a term, I'll call these replaceable components floor replaceable units. They are the components that you must replace as a floor troubleshooter. Now, how do you know what the floor replaceable units are? Well, you either know already, or you ask somebody, or figure it out for yourself. In most cases, you will already know whether the components are replaceable or repairable, or are part of some larger unit that is replaceable. This comes from experience. If you have doubts, ask your supervisor. If you must figure it out, start by asking, if this unit is bad, how can I get the system back online in the shortest time? Now, a circuit board is often a floor replaceable unit. A resistor on a circuit board is not usually a floor replaceable unit. This is basically because it takes a lot longer to locate a single bad resistor than to locate a bad board. Now, I said that circuit boards are often replaceable, but sometimes you may have a choice. You should ask the questions, how is the unit packaged? Is it easy or hard to replace? Suppose you had a control panel with 30 boards. It might take an hour to find out which board is bad, but only 5 minutes to locate and replace the whole defective panel which contains the boards. Under these conditions, it would be better to replace the panel and get the system back online than to troubleshoot down to the bad board. Another way to determine whether a part is replaceable is to consider what parts are readily available from stock. It may be many times faster to replace a part than to repair it, but if that part is not stocked, there may be a long wait to get it. Okay, I've listed 3 questions you can ask yourself to help decide whether a part is replaceable. You'll probably find it pretty easy to answer these questions on the basis of what you know already. But if you have trouble answering one of these questions about a unit, there are some sources of information available. You can always ask your supervisor, or there are several kinds of drawings that can be helpful. You can look at schematics, ladder diagrams, machine arrangements, and wiring diagrams. Each may show which parts are intended to be floor replaceable. If there is a parts list associated with one of these drawings, it will identify the parts considered replaceable when the system was designed. It may also be helpful to look at the actual system and see how the components are packaged. You can usually tell by looking whether it would be faster to replace a part or the next larger assembly that includes the suspect part. Now, so far, I've talked about 2 of the kinds of information needed for visualizing system flow diagrams: inputs and outputs, and replaceable parts. The third type of information is the dependency of the interconnections. In other words, you must identify where each replaceable component gets its inputs and where its outputs go. Unless a system is mainly mechanical, the best source of this information is the prints. In mechanical systems, the main source of flow information is usually the system itself. Okay, now let's talk about how to visualize the system flow diagram. I'm going to use a procedure which helps ensure that the entire system is covered. In using this procedure, it will be helpful to sketch the various parts of a system flow diagram as you visualize their position in the diagram. With a large system, it might be hard to remember your visualized system flow diagram as you are troubleshooting. The drawing will help you remember it accurately. As I said before, the sketches need not be pretty, nor must they contain all the exact details of the equipment. In most cases, you can sketch flow diagrams in general terms, just like the diagrams we've used in this course. This visualized flow diagram, along with the prints, will give you all the information you need to troubleshoot. As you get familiar with the process, you may be able to improve on this procedure. For now, however, just follow along as I outline this procedure. The first thing to do is to determine all the system outputs. What is the system designed to produce? What byproducts or wastes are created? What inputs to other systems are supplied by this system? These are the questions to ask to determine the system outputs. Next, find the major subsystems. Now, a major subsystem is a group of components that work together to accomplish one of the system functions. For example, A TV has audio, video, tuner, and power supply subsystems. A car has lubrication, cooling, fuel, powertrain, braking, electrical, and several others. Now, some systems may have no major subsystems, so you can skip this step. Typically, though, these are the systems that have only a few kinds of inputs and outputs. The third step is to start with one of the outputs and trace the flow upstream to one of the system inputs, or to one of the inputs from a different major subsystem, identifying replaceable components and flow as you go. If there is one output that's more important than the others, this would be the place to start. Let's illustrate the process by sketching at least a partial system flow diagram for the family car. For our purposes, the outputs of a car might be the following: wheel rotation and braking, directional control, produced by the swiveling of the front wheels, lights, including both the inside and outside lights, sound, including the horn and radio, heat, this includes the heater output and the cigarette lighter, ride and handling, this is the output of the suspension subsystem, exhaust, interior airflow, produced by the heater fan, instrument readings, including the speedometer and warning lights. The major subsystems of a car are drivetrain, which includes the engine and the downstream components that connect to the drive wheels, lubrication, electrical, cooling. This refers only to the subsystem that keeps the engine within a specified temperature range. We will assume that this car doesn't have air conditioning. Fuel supply, exhaust, braking, and suspension. Okay, now let's take one output and follow the system flow upstream. A major output for an automobile is the rotation of the drive wheels. This enables it to move from one place to another. Moving upstream from this output, we would find the wheels, the axle, the differential, the universal joint, the drive shaft, the transmission, and the engine. Now this is about as far as we can go within the drivetrain subsystem. Now, after completing steps 1 through 3, let's look at the fourth step. Identify the inputs to this system segment coming either from outside the system or from other subsystems. At the wheels, there is an input from the braking subsystem and the suspension subsystem. At the transmission, there is an input from the driver, who selects the gear ratios. At the engine, there are many inputs. Inputs from the fuel, lubrication, cooling, and electrical subsystems. The fifth step is to identify the outputs of the subsystem depicted. What does it drive? What does it feed? What does it emit? Well, of course the drivetrain drives the wheels, but this is already part of the system. It also drives the water pump, the fan, the fuel pump, and the alternator. Now the water pump and fan are part of the cooling subsystem. The fuel pump is part of the fuel subsystem. The alternator is part of the electrical subsystem. The remaining outputs of the drivetrain are the exhaust gases, which go through the exhaust subsystem to the outside air, with some going back into the carburetor through the PCV and the hot water for the heater. The sixth step is to trace back the inputs of your first subsystem until you get to the major system inputs. Do this for each of the inputs to your first subsystem until you have covered all of them. To show how this goes, let's pick the fuel subsystem. It feeds the drivetrain subsystem at the carburetor. Upstream of the carburetor is the fuel filter, the fuel pump, and the fuel tank. Notice that the fuel subsystem also gets an output from the drivetrain subsystem as well as providing input. The inputs from outside this subsystem are the gasoline that's put in at the gas station, the driver, who makes his input to the carburetor through the gas pedal and throttle linkage, and the air. that comes in the carburetor through the air cleaner. We mustn't forget the air. You may not realize it, but in terms of volume, your car burns many hundreds of times more air than it does gasoline. Okay, so far I have visualized the drivetrain subsystem and indicated its inputs and outputs. I have picked one of its inputs, the fuel system, and traced it back to its external inputs. When this has been done for each of the drivetrain inputs, you then go back to the drivetrain outputs and trace each one downstream to the point where it leaves the system. This is step 7. Now, let's take a look at the exhaust output. I wasn't telling the whole story before when I showed the exhaust gases going to the manifold. A truer picture would look like this. Some of the exhaust gases are fed back into the engine to be reburned. The rest of the gases leave the car through the manifold, the catalytic converter, the muffler, and the tailpipe. When all of the drivetrain outputs have been traced downstream, that completes the system flow diagram for the drivetrain. Next, pick another system output and trace it back until it joins the part of the system already drawn. For example, I might pick the light from the headlamps. This would be a good one because I don't have a picture of the electrical subsystem yet. Following the same procedure with the light output that was used with the wheel rotation output will give a complete picture of the electrical subsystem. I would trace the flow upstream from the lights to the battery and then trace all the inputs to and outputs from this system segment. Now, we don't have time to develop the full flow diagram for the car, nor is it always needed. You need only visualize those subsystems that you feel are involved with the malfunction. In the next unit, you're going to learn about localizing a malfunction to those components which can be suspected of causing the malfunction. When visualizing the system, your flow diagram need only show these suspected components and how they are connected to the outputs. But no matter how large or small the system, when visualizing you always start with an output and trace it upstream. Then you show the inputs and outputs of the system segment. In visualizing when troubleshooting, start with system outputs which are missing or out of tolerance. Trace them upstream to the inputs, then downstream to the other outputs. This process is repeated until the malfunctioning system is completely visualized. When you have traced back the last bad system output and have shown all branches that come from it and go into it, you have visualized a flow diagram of the malfunctioning part of the system, or possibly the whole system. Now, in this unit, we've used the automobile as an example of a system. But what about the machines in your plant? The process of visualization does not change, as you'll see in the practice exercises later in this unit. Now, in many cases, systems may be so large that even if you consider only their subsystems, you won't be able to remember the flow patterns in your head. When you have some free time, I suggest you look at your machine prints and sketch out a system flow diagram. It will be a valuable aid every time you have to troubleshoot that particular machine system. Now, in the next unit, you'll see how a system flow diagram is used to help you troubleshoot efficiently. Now, you're going to practice visualizing system flow diagrams. If you'll get your workbook and turn to the section for Unit 4, you'll find the exercise on system visualization. Now stop and rewind the videotape before removing it from the tape player.